Welcome everybody. My name's Dylan, and I'm here to talk to you about scaling from 0 to hero and using Cloudflare Workers as your only backend. So the logo for this talk is the little rust crustacean holding a sword, and the title comes from the fact that I really wanted something that scaled down to 0 when it wasn't being used, and then sort of like could also then scale up if it came under heavy load. And then it's also, we're talking a little bit about game development, hence the hero thing. So has this ever happened to you? Have you ever been wanting to play some board games with your group of ethnically diverse friends, but your weird hybrid of Monopoly and chess here only supports up to 4 players, so the rest of your friends are left wailing and gnashing their teeth because they can't join in. I generated quite a few different images for this slide, and I chose this one because it's the most horrifying. But in all of them, it generates this weird chess Monopoly hybrid. It must be like ChatGPT's idea of like the platonic board game. So maybe that could be an interesting idea for a game, is like where you buy up the real estate on the chessboard or something. There are a few games that solve this problem. So one of my favorite ones is Avalon, and it scales quite well up to 10 players. And it does so essentially by splitting you into 2 factions. And then the game runs for a maximum of 5 rounds, because essentially the 2 factions are sort of like battling against each other to either successfully complete a mission or sabotage it. But it only runs for 5 rounds. So if you're playing with 5 players, it still takes 5 rounds. If you're playing with 10 players, it still takes 5 rounds. Another one in that same vein is Secret Hitler, which probably more people are familiar with. I like Avalon a little bit more than Secret Hitler, although Secret Hitler does have the advantage of being able to accuse people of being Hitler, which is quite fun. But it's a similar thing where you split into 2 teams, and then the game doesn't scale with the number of players in terms of how long it takes to play. And lastly, Codenames is another example where you're splitting into 2 teams. So the thing that all of these have in common, well, maybe not simultaneous turns, but I couldn't change the wording on this slide because I'd already submitted it. It's more about breaking the linear relationship between the amount of players playing the game and how long the game takes to play. Because if anyone's tried to play like Magic the Gathering with like more than 4 players, it just drags on for hours. So in a traditional game where it's like you take your turn, and then you take your turn, and then you take your turn, as you scale up to a large number of players, it just becomes really boring because it's like an hour until your turn comes around again. Where's my presenter slide? What's the next one? So I think most devs have, where's my mouse gone? It's over there. Most developers have like flirted with the idea of game development, I think, because it feels a lot more appealing than building yet another CRUD API, which was my talk last year. And so when I left my job in December, I kind of wanted to like build my own game, and I was particularly inspired by this problem of I'm somewhat blessed with a larger friendship group. We all actually met working at a minimum wage job at a cinema, and 10 years later we're still friends. And as people have gotten partners and people's housemates have kind of been rolled into the friendship group, we do really have this problem where it's like when we all hang out, there are a few games that we can play. And so I was really inspired by this game from the 90s. I don't know if can anyone raise their hand if they recognize this game? Yeah, a few people. Okay, cool. I have talked to so many people about this, and they just have no idea what this game is. But my brothers and I used to play this a lot when we were kids. And it's called Quibble Race. And you essentially race these little green alien dudes, and you bet on them. But the thing that makes the game really interesting is you can buy these special items that affect the race in some way. So you can give them steroids or poison them, or you can buy like a bodyguard that like protects them from being poisoned. And you can only play one of those items each round. And so there's an interesting kind of like strategy where you've got to like coordinate with other players and sort of like gang up on a particular quibble or something like that. And it leads to some really interesting dynamics. But the problem is this is like a flash game from the 90s, and so you'd all be playing on the same computer, right? And being little kids that are little shits and cheat a lot, you'd be like looking over your shoulder to see what your friends were doing. And so I really wanted to make something like this, because I thought that this would scale up to a large number of players really well and would also sort of be a pretty fun experience. But before I immediately jumped into sinking 500 hours of development into this project, we actually needed to like play test and make sure that it was fun. So this is me dressed as Sailor Moon at the Christmas party last year, because it was a space-themed Christmas and Sailor Moon seemed appropriate. And so what we did was we made like these all these like cardboard or paper things, and we cut them out, and so we play tested out to actually make sure the game was fun. And so you can see a bunch of the items that we came up with. Basically, every rule in the game has some item that then subverts it in some interesting way. And my friend made these little, I don't know if you can see them, these little Play-Doh creatures down the bottom here to represent the little aliens that are racing. And yeah, it went really well. People had a lot of fun. Unfortunately, I really wanted to use like Monopoly money to track people's balances and stuff like that. It's nice and tactile, but out of all of my friends, nobody owned a copy of Monopoly, which is just crazy because every time I go into a board game store, it's absolutely filled with just a glut of like bullshit Monopolies. And when I was putting together this talk, I found this one. This is a real product that Hasbro made. Strangely, isn't in stock for the last couple of months. Can't imagine why. And so the other main inspiration for this game is Jackbox. If you've played Jackbox before, it basically works with you have a single TV in front of you, and then everyone uses their phone as like controllers, so you can do all sorts of stuff with like hidden information. But if you've also played Jackbox, you've also realized that the kind of experience of Jackbox is a bit shit. Like if you, it disconnects quite frequently. If you refresh the page, it kicks you back to the main screen, and it's really difficult to rejoin. But the crux of the difficulty of designing a game like this, where you've got a screen and then sort of like a bunch of mobile devices, is kind of like real-time multi-client state synchronization. And so that comes with a bunch of interesting engineering constraints. We've got like cost, latency, it needs to be like real-time, and I suppose latency and real-time are kind of the same thing. And it also has to be based on web technologies, because like if you're at a party trying to get a bunch of people to download an app onto their phone just so they can play this game that they may never play again, it's just kind of like a non-starter. So the clients really need to be like based on web technologies. And so that presents an interesting question about what does my backend architecture look like? And so there's a bunch of different solutions here. So I've kind of tried to illustrate the cost versus load problem for a bunch of different approaches. So we have peer-to-peer, which is free when there's low volume, free when there's medium volume, and free when there's high volume, because it's peer-to-peer. Like it just scales basically infinitely. If you have a dedicated, it basically scales linearly with the cost of traffic. Serverless starts off free. It's pretty low cost at medium, but when traffic gets high, it becomes really, really high, right? Because before anyone comes up to me afterwards like, did you know serverless actually runs on servers? Yes, everybody knows that. And so ultimately, it can't be cheaper than a dedicated server, right? Because it's running on a server, and whoever's providing that to you has to get their profit margin on the top of it. So it has to scale worse at high volumes than dedicated, right? The reason it's cheaper at lower volumes is because of shared tenancy. So you might think based on that peer-to-peer is the way to go, and you would think that if you'd never tried to implement peer-to-peer. So I have the unfortunate privilege of having worked on a peer-to-peer project before. I worked at Caffeine TV for a while, which is a kind of Twitch competitor, and they were all using WebRTC. So if you're LAN only, that's great, because then you don't have to deal with NATs and firewalls. If you're not LAN only, which in this situation you probably aren't, right? Because unless you want all of your friends to be joining your Wi-Fi network, and then it's like handing out the Wi-Fi passwords to everybody, they're probably going to be on their mobile networks when connecting to that. And these days, not only do you have people's NATs, but like I'm with Aussie Broadband, and they have a carrier-grade NAT as well. So you've got 2 NATs that you need to try and get through in order to establish the peer-to-peer connection. So we have a couple solutions for that. You need a stun server, which helps figure out what your peer on the other side of the NAT to each other is. And then if that fails, you need what's called a turn server, which is the kind of like fallback where it basically proxies the traffic through it. So it turns out peer-to-peer is not actually free, because you need all of this other kind of machinery there in case things fail as a fallback. And you also just get in this nightmare situation where someone has a modem that's still from the 80s, and it doesn't implement some like particular nuanced part of the stack, and it's just like, hey, it doesn't work on my crazy home network situation, and you just can't diagnose it. It's just, it's impossible. So the other main constraint is latency. The name of the conference, roll credits. The latency of peer-to-peer, so if it's LAN, it's awesome, because it's just, it's LAN. The worst case scenario for peer-to-peer is that you have to do a round trip through the turn server. The worst case for dedicated is obviously round trip to the server. So depending on where that is in the world. And then if you want to have lower latency, you'll have to do like a multi-region deployment, right? So you'll have to deploy that into multiple regions so that customers can connect to their closest thing. And when it comes to real-time, we have a few different options. So I said that we have to use web technologies. And people who have probably implemented actual games with multiplayer are probably cringing at the idea, because these are all TCP-based. And the first thing you learn about multiplayer game development is that you don't use TCP. And the reason for that is typically when you're making a game, you're sending the most recent state, right? And so if a packet gets dropped due to the unreliable connection between you, you don't care. You just send the new state, and you just always use the most recent one, whereas TCP makes the guarantee that you will deliver all the packets in order, right? So in the event of a packet drop, even though you sent the newer state, the client will wait until the older packet gets retransmitted before servicing both of them. So I think that using Edge, which I'll get into a little bit later, kind of mitigates some of the downsides of TCP because the reliability of that connection is only to the edge location. You're not traversing to the other side of the world. But even so, within the constraint of web technologies, we have a few different options here. So long polling, server-side events, and WebSockets. I really wanted to use server-side events. But this is actually a leaked photo of Jeff Bezos when he finds out that you're going to try and do persistent connections on serverless. Because like serverless and persistent connections are kind of antithetical to each other. Like the serverless, you get charged per, or at least on AWS, you get charged per second that it's operating. It's charged in gigabyte seconds, so it's the amount of memory that you're using for the amount of seconds that you use it. So if you want to hold a WebSocket connection open for, I don't know, like an hour-long game, like you're being charged for that entire duration, and you can't even. I think the maximum is like 15 minutes, if I remember correctly. So it would seem that our desire to do real-time communication is fundamentally at odds with serverless paradigm. So we're going to try and compare some of these solutions, and to do so, we'll use this example game. So we're going to assume there are 15 players, which is kind of the maximum number of players I've designed the game to work with, plus the one host. We're going to assume that users send about 100 messages, so 100 events to the server per game, that the game runs for about an hour, and we'll assume generously that you've coded really well-optimized code and that you're using minimum RAM and CPU, and et cetera. So the pricing of Lambda this is taken from US East. It obviously varies between regions. Apologies for the scientific notation, but I had to try and like fit it into a very small space. So the free tier is 1 million requests per month and 111 gigabyte hours. So that's how much memory you can use for how much time. The paid tier is then 2 cents per million requests and 0.054 per gigabit hour. And the Lambda times out after 15 minutes. So trying to hold a WebSocket connection open on a Lambda is a terrible idea. Using our example game, you would run about 60 games per month for free before kicking into the paid tier, and then it would cost you $100 per 1,000 games. I introduced this new scientific unit, a killer game. Those of you familiar with AWS might be cringing with my attempt to use Lambda for WebSockets, and you would be right, because API Gateway actually has a feature where it can manage the connection for you. And so API Gateway defines a message, which it will charge you for, as a 32 kilobyte chunk. So if you send a message that is larger than 32 kilobytes, you will be charged multiple messages. It also charges both for incoming messages and outgoing messages. So if you have 16 clients and one person sends a message, you then get charged 17 times, one for the incoming message, and then 16 times for the fan out over the sockets. I don't know if I'm reading the documentation incorrectly, and perhaps someone from AWS can heckle me. But my understanding is the free tier is only for the first year. It doesn't refresh every month, nor even every year. It's like if you don't use it in the first year, it's gone. And once you use it, it's gone. Anyway, it doesn't refresh. Like everything else has like a monthly free tier, but like the WebSocket stuff and API Gateway is like the first year. So I don't know if that's misinformation, but that was based on my reading of the docs. So the free tier, once again, is 1 million messages. But the thing that API Gateway will do is it will charge you for the length of time that the socket is open for, right? So leaving a socket open, doing nothing, costs you money. And you can you get like 12,500 hours in the free tier before it expires, and then it's 25 cents per 16,000 hours. Man, this scientific notation is kind of hard to read. I regret using it. And then $1 per 1 million messages. So using our example before, we get roughly 600 games in our free tier, and then it's $1.84 per killer game after that. Plus, the way it works is API Gateway will emit events to you based on the WebSocket state, and then you have to do something with those events in order to track connections. So you have to do some yak shaving in terms of building finite state machines that write state into DynamoDB in order to be able to track connections. And so you'll have some DynamoDB charges, but I suspect that they would comfortably fall in the free tier. So it's not too much to worry about. So the other thing is, this is AWS's regions and edge locations. So all the yellow ones are the regions. And the blue ones are the edge locations. And the functionality available to you in the edge locations is extremely limited, right? So your users connecting to this game are going to have to relay to one of these yellow dots, assuming that you've done the insane thing of deploying into every single AWS location. Or if you're lucky enough that the functionality that you're using is present in the local zones or like the edge locations so that you can relay through the edge. Alternatively, this is Cloudflare's edge network. So just to like flick between them a little bit, slightly different projections, but it's a lot more dots, especially in Africa, which the Mercator projection makes look really small, but is actually enormous. So there's even one in Adelaide. Isn't that nice? So this is Cloudflare's edge network. So this is the meat of the talk, Cloudflare Edge Workers. So this QR code is a link to the talk by one of the distinguished engineers from Cloudflare, whose name I am not remembering right now. And he talks all about they wanted to start letting users run code in their edge locations. But the existing technologies in terms of containers and VMs and stuff like that, based on their calculations, they needed like 100x efficiency gain to make it viable. So they kind of like looked around and looked at the security problems, like running foreign code, needing to have multiple lightweight threads, and they kind of realized that the browser had already conquered a lot of these problems. And so they actually decided to use V8 as the kind of primitive of the runtime, rather than something like containers or like Firecracker or something like that. And so that does mean that it is JS and WASM only. And that may seem like an extreme restriction, but if I have enough time, which, oh shit, I don't, I only have 8 minutes left, then I will get to that. So the other major difference is Cloudflare will charge you based on CPU clock time, not wall time. So if your Lambda is sitting there doing nothing, in terms of waiting for I/O, you get charged for that. Whereas like Cloudflare, it's CPU clock time, so you don't actually pay for I/O wait. Skip through this a little bit, skip through that a little bit. You can download the slides later if you want that. So in terms of the edge workers are great, but if your state is still living in a region, then you still have to make the round trip to it. So what are the options in terms of edge compatible state? So D1 is like an SQLite compatible data store. It has some annoying limitations so that it's single writer. So that means that all your writes have to go to a single node. It does this weird thing with transactions where you have to use JS stored procedures. And if you want to not get stale reads, you have to use transactions, because otherwise you'll get routed to potentially a read replica. So it's not great unless you really want SQL. KV is the key value store. It's eventually consistent, but it's globally replicated to every edge location, so it's really low latency. And then finally, we have durable objects. And the reason I had a bunch of question marks for durable objects on the previous page is because durable objects are really weird, and I have no analogy to draw with them. They are a global singleton JavaScript object, right? Which is supremely weird. And so there will be only one instance of a given object anywhere in the world of a particular ID, and all of your, it will move around dynamically based on like where traffic is getting routed to it. But you can use that as a single coordination point for things, right? So it has both ephemeral in-memory state and also durable transactional key value store. So because I'm running low on time, I might skip through a bunch of these code examples. But this is just like a basic kind of thing. Like if you've written Lambdas, you're familiar with this. The REST request comes in, you send the response back. Skip through that. If you want to route a request to a durable object, you have this thing that comes in. The durable object has a namespace. You pass an ID, and then you forward the request to it. And then on the durable object side, so a real-world example is you would typically pull some parameter out of your route and then use that to dynamically route to which durable object you wanted. So this is real code for my game, where based on the lobby code, it gets routed to the game ID with that code. Basically, the durable object, when receiving the request, has a very similar thing. Takes the request, returns the response. You bind the name of the class, like of the JavaScript object, to make it a durable object, which you can do that way. Sorry, we can skip over the Rust examples. So the object can have ephemeral state. So long as the object remains in memory, the state will be there, but it gets evicted after 10 seconds if it's had no activity, or if potentially in an out-of-memory situation, it can get evicted sooner. So it can be useful for stuff where you don't care. So maybe like a rate limiter, where it's like 10 seconds. Like your rate limiter probably doesn't span over 10 seconds, so you can just use ephemeral in-memory state, because if it drops out of memory, it probably means that the rate limiters drop back to 0 anyway. You also have durable state. So it's a simple key value store. So this is a simple counter example. We grab the count out of the key value storage, increment it, and then we respond hello world with the current count. And astute observers may realize that there's a data race here because we do a read and then a write. Cloudflare do a bunch of really clever stuff with the storage where it's like once you do a read, it kind of does this implicit transaction stuff. You can read about it more on their blog, but it's pretty cool that they protect you from some basic errors like that. Skip through the Rust. This is some code, real example from the game. You can read it later. Oh yeah, so that's cool, but what about the WebSocket problem? So, Hibernatable Web Sockets. This is the key to make the whole thing work. Once you call the API to accept the WebSocket, it is free to hold the socket open forever. Like, you do not get charged any kind of duration charges. Furthermore, you only get charged on incoming messages, not outgoing, which means fan out is free. So that means that you, if you've got n users sending m messages to n users, that's normally n squared, right? Complexity in terms of cost. But this breaks it down back down to linear, so that's great. It also has free support for heartbeats, so you can set up an auto response like ping pong type thing. That's free as well, don't get charged for that. You can also tag the WebSockets with metadata. Oh yeah, so this is all the code you need to do fan out like relay server, right? So the incoming WebSocket is accepted, and then when we receive a WebSocket message, we just iterate all over the WebSockets and send them out to them. So that's all the code you need to do like a chat room. That's it. That's all you need. And that's pretty cool, if you ask me. Connection metadata, skip over that. OK, that's great, but what about my static assets? So the recommended way to do that is to use Cloudflare pages. So all of your static assets are free when requested. They're already behind Cloudflare's DDoS protection. But the project is in an awkward transition phase away from Cloudflare worker sites, which I just skipped over, but you can read that later. So there's like weird limitations where it's like a Cloudflare pages project cannot directly create a durable object. You need a worker to create the object and then bind it into the Cloudflare pages. And this isn't documented anywhere. I had to go into their Discord, and then there's like a bunch of people asking this exact same question, which is how do I create a durable object for a Cloudflare page? So the project is still very in this weird transition phase, which makes it a bit horrible to work with. But this is basically what you do. You say, what do you want to route to the worker, and what do you want to route for static assets? And all requests to those static assets are completely free, which is awesome. So this is the final architecture. So we have the Cloudflare pages. We've got the static assets and the workers. The workers will forward API requests to the durable object. The durable object holds all of the WebSockets and then forwards those events out to each of the clients. And then we also store that event log in the transactional storage so that when the durable object drops out of memory and it gets resurrected, we then rehydrate the storage from the event log. When a client disconnects and reconnects, we push the entire event log down to the client. So we have like a really easy resumption of state. And then the client has the code to build its own projections or read models over that event log, which is pretty cool. And then just quickly some bloopers / behind the scenes. So this was the very first quibble that I got racing. I've never done any 3D programming before, so this was quite the achievement to get this little free asset jumping along. And then the GIF compression has completely destroyed this. This is some multiple little monsters racing each other. This is when I first moved to using the to using Blender to compute the scenes and then importing it. Every game and graphics API uses a different up direction. Like some of them use Y up, some of them use Z up. Some of them are left-handed coordinate systems, some of them are right-handed. So when you try and import assets between things, it just gets all messed up. And you have to write a lot of code to fix that up. Similar scaling problems. But yeah, summary. It's worth looking outside of AWS sometimes. You know, Cloudflare are like edge first and then are building a platform as a service. So they're coming at it from the other direction, whereas AWS is platform as a service and then kind of like building towards the edge. So like everything Cloudflare does is edge native first, whereas like AWS is kind of like realizing that edge is exciting and kind of moving towards that. It allows for some really great UX in terms of latency, and it actually scales down to 0. Oh man, I was hoping I'd have, so these are 2 great talks on WASI and WASM. Really wish I had more time to talk about them. But if you're not aware of WASM and WASI, I think this is really going to change what cloud native deployments look like in the next 10 years. And they're not quite ready for prime time yet. They're still in stabilization. But once they are, they're going to be really big. And so I'd really encourage you to check out these 2 talks because they're super exciting. And it solves a whole bunch of problems that have been touched on today. If you want to know more about that, come talk to me after this talk. And yeah, lastly, the game is called Deep Space Derby, and I was really hoping I'd have a demo ready for today, but unfortunately I had to focus on the slides since that's what you're here and what you paid for. But if you'd like to follow the development and have access to the early beta and have feedback, please come and hang out in the Discord, because it will be ready soon. All right, any questions? 0 seconds left.